I'm gonna wait another 2 minutes because people are just signing in right now.
Am I muted?
Oh, nope.
Oh, I shouldn't be, or should I?
It doesn't matter. I'm just gonna speak and then pass it over. Okay, so we're gonna get started now. Thanks everyone for joining us today for ACI-Ontario's Fall Concrete Webinar Series. We're really sorry that yesterday's session was postponed because we had some technical difficulties, but we hope that if you signed up for the Stubbies precast session, you'll re-register for the webinar tomorrow at 2:30. This year we aren't able to feast on lobster as we usually do, but we still wanted to host some interesting technical sessions to keep the momentum of our chapter going. We thank you for your support during these challenging times. Some quick housekeeping rules. We have 2 presenters today, and we will wait to address questions at the end of the presentation. Everyone will be muted for the entire session, so if you have any questions, just type them into the questions pane. Today, we're going to have Lloyd Keller from Ellis-Don and Nick Beristain from Prairie Materials talking about modular of elasticity. So now I'm going to hand it over to Lloyd.
Can everyone hear me?
Yes.
Okay, perfecto. Okay, welcome everyone. This is a bit strange, a bit different. I haven't done online like this a lot of times. Usually I'm in front of a big audience, so you can sort of look at the faces and see what's going on and try to interact. So we'll have to do this without that process. So hopefully we're still able to give that kind of a presentation and give the information we're trying to do. Again, my talk is MOE why and how, and MOE is obviously modulus of elasticity. Hardened properties for concrete have typically been mostly limited to compressive strength, airvoid spacing, and RCP ratings. Other properties that are more regularly tested include shrinkage and ASR reactivity. Properties like modulus of elasticity have been much less called for in the materials testing program. A reliance upon its values being a function of compressive strength or empirical has until now been much more the norm. This appears to be changing, and now engineers are much more requesting that these properties being measured. So, what am I going to talk about today? Well, we're going to do a little bit of an introduction on what is modulus elasticity and the different types or ways of modulus measurements. Mostly, we're going to be talking about one type. Another thing, why are designers concerned with MOE instructors? And we're going to go through a little bit of how MOE or modulus elasticity is a predominant factor in the predictability and in the precision of the values and the performance of the individual structures. And so it's a very important attribute to know. I'll explain a little bit more also about the ins and outs of it. We have some example projects that we're using, which I'll allude to and I'll talk to when we're doing our presentation. And another item is how does it relate to strength and what are the critical values in determining MOE and which ones are the factors that can contribute. Okay, so here we are, and you always, anytime you want to talk about something like this, you got to have graphs and charts, right? It makes it look sort of cool, and you can sort of figure out how things are working. what you have here is we have a graph, stress to strain and the relationship. And essentially modulus elasticity is the slope of the line between stress and strain and its reaction point. What we have here too is if you look at the graph, you have right at that intersection between the red and the black, you have the elastic region, and then you have the plastic region, which is the plastic region is the red, and the elastic is the black. The elastic region is typically linear, and so there's a linear relationship in the relationship between stress and strain. Once you get into the plastic, it becomes nonlinear, and then it becomes a more difficult area to predict. And then you get to the failure point, where essentially the ability to take on any more strain is stopped, and you get a failure in the material. So factors that can attribute and affect the modulus of elasticity include the strength of the concrete, the cement paste factor, the aggregate type, the concrete wetness condition, the transition zone between the aggregates and the paste, mixed proportions, concrete age, and curing regime. What this next slide here essentially is talking about, again, there's modulus elasticity are three types: Young's modulus, shear modulus, and bulk modulus. Okay, the one that we're typically dealing with in most cases for what we're talking about right now is the Young's modulus, which is the ratio of the normal stress to the longitudinal strain. And you see essentially putting a load onto it, and how does that affect the length. So you see as the fellow is trying to pull the cylinder from the wall, what he's done is he had an original length. This is a pretty strong guy too, and what he's done is he's made a change of length, which is the effective movement or displacement due to an applied stress or load. And so this relationship is the Young's modulus. Shear modulus is another, and essentially is defined as a ratio of shear stress to shear strain. So so when you're looking at this, if I'm a structural engineer, I would probably be looking at this if I'm concerned about the displacement or sway of a tall building under wind loading. Bulk modulus elasticity is referred to as the incompressibility of a substance is a measure of a substance to withstand changes in volume when under compression on all sides. And it's equal to the quotient of the applied pressure divided by the relative deformation. And there's a neat little graph there showing, or chart showing what that is equivalent to. I only bring these up because there are different means of measuring modulus, and just so you're aware of that. But again, as I was saying, the major one that we're going to talk about right now in this session is the Young's modulus. Okay, so the next thing is why are we concerned about this, and what does it do for our how does it implicate or impact our building or our designs? Well, if this thing works, it may. Oh, there we are. Okay, so first of all, if I go into A23.3, which is the design code for concrete, I note that in modulus elasticity is defined, as you see here, is modulus elasticity and compression is used in design shall be taken as the average secant modulus from a stress of 0.4 F prime C determined for similar concrete in accordance with ASTM C649. If the modulus of elasticity is critical to design, a minimum value of EC shall be specified and shown on the drawings. That's an important attribute. Why the 0.4? In case you're wondering, that's because that, if you remember the graph I showed earlier, that's the elastic region of the concrete. And so when you displace that, you can expect it to come back to its original place without any permanent deformation. And again, there's a note. If the modulus of elasticity is critical to the design, the designer shall establish whether such concrete can be produced. It's an important attribute to discover. And this is where we're getting into the realm of making sure that you actually measure the properties of the modulus of elasticity rather than use some empirical value or some function of F prime C to determine it. Okay, and I'll show you why in a moment. The other part to consider is in lieu of results for tests of similar concrete, they give you a couple of algorithms as which to determine the MOE. One being depending if your yield is within that range, and then another one when the strength is when the strain is within that, and when the strength is that. You do another equation. The value of EC is affected by aggregate fraction in the mix. The modulus of elasticity of the aggregates and the loading rate. The modulus of elasticity of Canadian concretes would generally be between 80 and 120% of the values seen in clauses previously described. So it's pointing to, and why I bring this up, this is pointing to the fact that there is a means of measuring from empirical values, but that these are not accurate, and the numbers that they put in the code in the note is between 80 and 120% of the values. We have information to show through trials and measurements and whatever that actually it can be a lot greater than that, also up to 30 to 40% differential. So it's important to know that, and so you recognize whenever you're doing your calculations or you're doing your assessment of the performance of the structural element, you can be out by that factor as far as the accuracy of the readings. This is a chart that we did in-house of measurements of MOE relative to strength for a number of different projects that we have been working at over the last number of years. And the black line or the gray line shows you the theoretical modulus of elasticity based on the empirical values that I previously showed. And the numbers, and then the points here are measured values, and it shows you how much you can get a variation between measured values and theoretical. It also shows that so there is a wild fluctuation, and a lot of the part is a major part is the aggregate types that you choose and the strength of the aggregates and how there was this movement and everything. So it's important to know that, and that's why it's very important to measure. And to usually what this is done, this is a pre-qualification that's done, if you remember back when in the previous slide, where it's the responsibility of the engineer to know if it is important, that in fact what he has to do is he has to ensure what kind of modules can be made. In a lot of these projects that we worked on, we did the pre-qualification testing with various types of aggregates to determine where in fact what we can achieve with the basic types, and adjusted and modified to the point where we got something that was achievable from what the requirements of the engineer were. Typically, in general, the sedimentary aggregates are less stiff than the metamorphic or the igneous, and that's a little bit of a way to go by it. Also, your density of your aggregate has a big part and contributor to performance. Also, the denser the aggregate, usually the better your modulus elasticity is. Okay, so now we're getting into a few areas where modulus is used from a design perspective to predict what the net deformation would be based on the type of structure you're talking about. So what we have here is I've pulled out again in 23.3, and this is for slab deflection and how you can measure the performance. And there's some of the critical things to decide here is MOE measured and confirmed in production versus using as a function of F prime C. Note that the time-dependent values for MOE are to be measured using concrete specimens versus a factory value from F prime C, which determines stripping or form removal. So that's in this part here. So slab thickness required may be used, and the nature of restraints at panel edges. For deflection calculations, modulus elasticity for concrete shall be specified as clause 8.2. Moment of inertia, shrinkage, and creep are also factors that you build into your equation. Next. Okay, for slab deflections, note the importance of F prime C in the equation for slab deflection in the red arrow. So this is the normalized overall equation that you would do as a simple beam movement. And note that the modulus elasticity is in the quotient, and obviously an effect or a variable time of 10 or 20% would affect your values of your net calculated deflections accordingly. What is typically done though is it's called for deflections in slabs, they use what's called the equivalent frame method, not simply just a simple beam, and that's a summation or a combination of various movements through various zones of the slab, and whether you be in the column zone or the mid zone or whatever else, and various stiffnesses. And then you use the equivalent frame method in your FEM programs to rationalize the summation of all these movements to get at what your net slab deflections would be. And so with the advent of the digital programs and stuff that we have now, we're able to do this. But again, MOE is one of your prime contributors to determining what this number is. Okay. As an aside to that, this has been a big issue with our since I've been working on CSA, which is some 25, 30 years or whatever. Always the tolerances and movements and predicting what slab movements are going to be has always been the bane of our existence, and it's always been a very difficult thing to do. And so with this edition coming up, which will be 2023 published, we have decided to develop an annex, which is essentially a more extensive best practices guideline to summarize what the contributing factors of slab movements are and how they can be optimized or conditioned to the point where we can be more precise in our predictions by limiting the variations and the inconsistencies. This is the introduction, which for elevated slabs and building construction best practices. I'll just read out just quickly the introduction, but the construction of elevated slabs in commercial operations has progressed through a continual conflict between what can be predicted and what is practically buildable. Formwork practices or composite action between the metal deck and the fresh concrete element are being produced on an elastic supporting system that is finished with mechanical screeds and trowels. To determine a realistic tolerance of the surface profile and the overall thickness has been a challenge because of the limitations of the techniques and the consistent reporting and recording of the cause and effect of this profile due to the methods. Our best practices guide has subsections which include formwork setting, concrete placing, reinforcing setting, post-tensioning, design approaches, and sensitivity to empirical versus calculated approach, including materials choices, measurement and case history examples, materials properties like creep, shrinkage, tensile, strength, MOE, etc. are important in working towards the calculated approach. So we've got this is going to be a very extensive section. It'll probably be between 10 and 20 pages, and it should help the practitioners in the various areas to work towards something that is more comprehensive than is available right now in the industry and throughout literature, which is why we're writing this up now. Okay, moving away from slabs, we now get into high-rise construction, and with the advent of skinny, super high buildings, especially for residential buildings in dense cities like New York City, the requirements for very high MOE, up to 125 gigapascals, is making control of concrete mixes and selection materials extremely important. Reliance of the dependable results allows the engineer to design a structure that will resist wind loads from wind and say high modulus aggregates like trap rock and basalt are chosen for the stiffness and ability to provide a high modulus concrete product. And this is basically a rendering. Some of these buildings are there now, but it's a rendering of all the potential high-rise buildings that are coming in place in New York City. And as you see, these are clustered around Central Park, which is in most cases, these are all residential buildings and very tall, but with a width to height ratio of 1 to 24. So you've got a very tall, slender building. And obviously, in order to resist the sway, there's a significant amount of engineering that has to go into it to make sure that, in fact, these things work. But this is one of the things leading to the requirements for this much more sophisticated design method than we've gone in the past. This is the project that Station and I worked on for about 3 or 4 years in Bogota, Colombia. It is a project that was designed from an architecture by Rogers and Stirk in London, and the structural design was done by Arup in London. It's a 46-story concrete core and perimeter exoskeleton. And one of the critical criteria for performance was to ensure that the floors would be level and flat, allowing for the loading and movements of the core relative to the steel and the concrete columns around the perimeter. So this is what you see. There's Atrio. It's now completed. And there's going to be a second tower over here, which will, the Atrio one right now is 46 stories, and the second tower will be 64 stories, which will go right over here. It's nestled nicely and beautifully in the back between the Andes right here and on the footsteps of Bogota. This is the central core, and what you have is 2 diamond-shaped floor plates, and you have perimeter combination concrete and steel columns that are supporting the floors. So you see that the loading has to be tied so that in fact we can ensure that the movements between the support off of the core and off of the columns and the steel and whatever else, we're going to get equivalency. So the floors don't end up being sloped as we get further up. So this is an excerpt from the design process manual that Eric developed, and to make sure that the floors and the materials are accurate and consistent. And one of the key elements here is with ensuring that differential shortening, which is a phenomenon by which columns and walls and tall buildings shorten by different amounts. If not accommodated for differential axial shortening, it can result in a floor which is not level. And as he describes here in his outline, there's 3 reasons for this. One, differential axial stresses in the adjacent columns mean that they will shorten by differing amounts when first loaded. Concrete columns and walls will tend to shrink over time as the concrete dries or cures out. Steel columns will not. Additional concrete columns will continue shortening even after the load has been applied, a phenomenon referred to as creep. The combined result of these 3 effects is that constructing a flat floor requires a considerable degree of skill and care. The effects become more pronounced in tall buildings over 10 to 15 stories and in buildings where there's a mix of concrete and steel. So Atrial was specifically that. In Toronto, we also over the last number of years built the Bay Adelaide Center, which was similar type thing. It's steel columns around the perimeter and a central core in the middle. And similar project we just completed, which is in the CIBC Square in downtown Toronto off of 81 Bay. So this is something that has to be looked at and contained. So what is done? Certain columns will need to be preset to compensate for the elastic shortening, creep, and shrinkage that will occur during the construction. So what does that mean? Well, it means that these have to be preordained and described based on the properties of the materials to understand how we're going to compensate for these movements, and it has to be predicted. So the success associated with presets can be improved by utilizing appropriate analytical model for the structure, using the best available estimates of material properties, and ensuring consistency in the materials properties, for example. So here we're from their design standard. Again, these were the parameters that were considered for generally setting the levels and floors of the atrial. And so we've got 14 items, of which some things include elastic modulus. So there was a predicted value, and so we had to make sure we hit that elastic modulus and within a certain range. We had to identify the relative humidity, the time of loading, ECT model for creep and shrinkage. So what was doing is we figured that the ultimate loading would be around 150 days. So what we did is we did the predictor of what the effects of creep and shrinkage would be at that particular point in time, and then the engineer developed his modeling and his prediction models for the preset. What we have here is this is part of the quality control that was involved in Atrial, and as I said, we had to stay within a range of the modulus of elasticity so that we could ensure that in fact the movements were predictable. And so what we did is over time, so this chart here shows the measurement of the modulus versus the construction periods that we were working on. So we would take over periods of the construction, samples of the concrete, and measure the modulus of elasticity and hope to stay within that zone in that region. At the first bits, there was a bit of problems with it, and I'll let Nick describe a bunch of things from quality control and what you have to do to constrain that, but suffice it to say, Station and I were very busy in this stage, working through with Cemex, that was the ready mix producer, to constrain his quality control, to the point where we had consistent values. And also the other thing was to ensure that the testing was done properly, so that in fact we would get a number that we could rely on. These were just two graphs showing the effect of different aggregates that were surmised to use, and how the modulus changed over time. And so we used that as a basis for selection of the materials. Another area where we use MOE and hardened properties measured much more than we used to is in preparing for our thermal control plans for mass concrete. You'll probably be aware in CSA 23.1 that what we've done is we've gone on now to a much more explicit means of measuring for mass concrete and predicting our thermal control plans. The requirement on that is that we measure a number of properties, modulus of elasticity, coefficient of thermal expansion, splitting tensile strength, compressive strength, heat of hydration, whatever, to come up with a prediction value to which we can develop a thermal control plan. And again, the estimated value for strain capacity, which is one of the things we have to measure, strain capacity versus developed strain to work out what the net effect of thermal gradients are. And the strain capacity is a function of a ratio of the tensile strength to the elastic modulus. So again, we have to use MOE as a measurement for that. The tables above represent a process to determine the safe thermal differential that can be accommodated by a particular concrete mix based on properties for MOE, tensile strength, and coefficient of thermal expansion values that have been measured in advance. So what we've done here is, from working out the relationship of compressive strength to modulus of elasticity, we've developed over time how the modulus changes. Same thing with the splitting tensile strength and the direct tensile strength. Ultimately, what we do is we want to have a safety factor of about 1.5, which is the rate of the thermal cracking index, which is the predicted strain. Sorry, it's the strain capacity over the developed strain. So we want to have a lot more capacity than we do with the developed strain. So we were trying to go in about a 1.4 safety factor. What we would do with that, we would work out to get to a 1.4 safety factor on the right side of the table here. Then running across would tell us that would give us a temperature differential variation of 30 degrees C is what we could go with. And the factors that so the developed strain and the strain capacity and that. So that's what we're using to develop that. So again, modulus of elasticity is an important part in this measurement. Okay, this is the part you want to hear, the conclusions. Presentation showed a number of areas where measuring MOE enhances the precision of a predicted performance for deflection of elevated slabs after formant removal and short-term loading, predicting elastic shortening between differing materials and supporting structures, limiting the sway or lateral movements of tall and slender buildings under wind or other translational loading, and predicting safe temperature differentials in mass concrete during casting and exothermic cooling. It's important to have consistent properties of these materials and ensure their quality control program is in effect to maintain the variation within acceptable ranges. It is important to measure the potential MOE and pre-qualification testing in advance of writing project specifications when MOE is important to the performance of the structure. This is emphasized in our design codes and should be included as a part of the overall construction plan. Thank you very much.
Awesome, thanks, Lloyd. We are at about halfway point, so I'm gonna turn it over to Nick now. and we'll do questions at the end.
All right, let me get set up here real quick. All right, can everyone see my screen?
I don't think so.
I can.
It says, oh, there we are. Now we can see your screen, but the speaker notes screen.
Okay, let me change that real fast then.
There we go.
There we go.
Yep, there's that.
All right. So my name is Nick Beristain. I am the quality control manager for Prairie Materials. I was asked to speak by Brian Schultz, who is one of my counterparts at CBM. We've had a long, good working relationship together, and he said, I think I know someone who might be able to talk a bit about the producer's perspective. And so here I am. So like announced before, I'm happy to answer any questions afterwards. Hopefully you guys enjoy the presentation. So to begin, just to give you guys an overview kind of the Chicago market where we primarily focus, we do about 270,000 meters annually within what we would consider the high-rise market. So that would be a lot of quickset, post-tension, high-strength concrete, usually within the downtown sector, although we are seeing a bit of a spread on that right now into newer areas that, albeit before COVID hit, we're starting to see a more vertical traditional living style. And we generally break this down within anything from 55 to 135 MPa. To give a bit of perspective specific to modulus of elasticity, the specification within Chicago building has come and gone a few times. In the early 1990s, the building you can see here on the left, which is 311 South Wacker, that was really the first building within the Chicago high-rise market that started to specify any sort of notion of modulus of elasticity. For that, they simply took the calculation from ACI and didn't do any actual testing. Jumping forward to the early 2000s when Trump Tower was built, this one initially started with a floor-by-floor testing of modulus of elasticity, but due to financial constraints, they eventually did also switch to the ACI calculation. So we had already built up a library at that point showing specific data and that we could meet the requirements, but in the end, it wasn't utilized and they simply used the ACI calculation. Jumping forward to when I was much more prevalently involved in the industry, in 2005, we did a project called 151 North Riverside. And although the building itself is not very slender, you can kind of see from the bottom here that it actually V's in. So that is to fit it between the Chicago River and the train tracks on the other side. So this really was the first foray for us in recent times into modulus of elasticity testing. Once we were starting to get into that level of construction and as we started to see more projects coming up, we evaluated internally what we thought we could do both in terms of local resources and our previous knowledge. And at that point, we were very comfortable delivering 45 GPa modulus of elasticity rated concrete for these projects. With that, we felt in particular because of the huge cost constraints that our materials put on the final product of in-place concrete, that could be done without deviating from our traditional raw material supplies or bringing in not necessarily foreign, but material that was well outside of our market. The biggest concern for us, though, because it was the hardest for us to actually prove, were constructability requirements. Could we simply produce this concrete and continue to hit our normal stripping times, our normal pumping rates, or were we going to have to drastically adjust our contractors' expectations in order to deliver this very stiff, very difficult to work with occasionally type of concrete? And so here on the left, you can see, and I'll talk about this project a little bit more. This was the Wanda Vista Tower. This was the next big project that kicked off after the previous project, 150 North Riverside, with a heavy modulus of elasticity. And much like Lloyd had shown, this is Grant Park in Chicago, right in downtown. And many of these buildings, I'll talk about this one, this one's called NEMA, have either started work or are out for bid right now. So even through the pandemic, we're still seeing a lot of this work come out if it had already gained some seed funding going forward. Again, just for a bit of perspective, nearly all concrete placed within the city of Chicago, especially the downtown sector, is placed using large stationary pumps. We rarely see truck pumps just because contractors know that these jobs are going to be 12 to potentially 24-month contracts with a lot of concrete being placed. So anywhere from 2 to 3 individual pumps, potentially even secondary pumps on higher levels as we get into higher levels. But most contractors have been able to utilize a single pump at 1 or 2 pumping locations to place nearly all of these buildings. So to jump to some specific projects, I'm going to touch on the different projects so you guys can get an idea of what we've experienced and then also what we've kind of learned from each of these individual projects or collectively through our testing of the materials. So the keynote project that we've had, it's recently been completed. It was completed early this year, was the Wanda Vista Tower. This is now the 3rd tallest building in the city of Chicago. And it is the tallest reinforced concrete building, slightly taller than Trump Tower in terms of the overall building height, but Trump Tower has an antenna on it, so it still has the overall height. It was built as 3 completely separate towers, and it required modulus of elasticity stepping down as you go up the building pretty roughly in thirds of 48.3, 41.4, and 37.2. We were very fortunate on this project, and along with the next project I'm going to show you, that we were able to work with an independent testing lab who we had already established a good relationship with. And I can't emphasize enough how important it is to have a good open relationship with the lab who will be doing the on-site testing for the ownership of the building. It can help eliminate so many problems going forward, and it can also just keep you very well informed of any potential constructability or overall performance criteria you might need to adjust within your individual mix designs. The next project, and the one you could see from the 2 renderings here, was completed late 2019, and this was NEMA Tower. It originally had a different name, but now the owners have changed it to NEMA Tower. This sits on the south section of Grant Park in downtown Chicago. Very similar in terms of overall modulus of elasticity ratings, requiring the 48.3, 45.5, and finally 43.1. This building was slightly more slender than the previous building, so that's why the higher numbers continue up through a higher floor value within the tower. But both this building and Wanda Vista were overseen by the same structural engineer, so it was very nice to have that consistency as these 2 projects essentially ran concurrently with very similar mix designs and identical testing. The lab of record on this was also the same lab of record who we worked with extensively on the previous project. So we felt that this was a much better project since there was so much familiarity for us in terms of testing, what the structural engineer required of us, and it was actually also the same contractor as well, so what their construction requirements were. This building was a bit different. Wolf Point East is nestled along the Chicago River. It actually just completed early this year, about midway through 2020. And now, although you can't see it right now, this park is actually gone because they're building the final tower, which will be Wolf Point South or Salesforce Tower. This was done with a different contractor, Walsh Construction, and a different testing lab. But the unique thing about this building was where the other 2 buildings had post-tension concrete decks throughout the entire building. This one was actually modulus of elasticity primary structures, followed by lightweight concrete for all of its decks. So it was all pan-filled decks. This one, again, was still developed by the same structural engineer. So you can kind of see the pattern here of a high 40s, bottom third of the building for modulus of elasticity, followed by a slight drop, and then finally the top out of around 40 GPa. 110 North Wacker was the most recent project we've completed. It was completed about 3 months ago. It also was modulus of elasticity primary structures, followed by lightweight concrete pan-filled decks. This one had much lower requirements because it was only, I believe it's only 55 stories in total. And it's actually framed by this very impressive, you can't really see it right here, but you can see it better here, completely open main lobby. This is the only building of all I've shown you so far that is not primarily residential. This is entirely office space. So this was a bit unique in the Chicago market, and it did not have any primary living space incorporated within it. But a lot of the same functions. Again, this one was placed using a single stage pump at the bottom. Actually, this is Wacker Drive, so it goes underground for about 30 feet, which is where they had set up the pump. So throughout all these major projects, I just kind of want to share with you a bit of an overview for what we had learned, and specifically as a producer, what can help you should you run into issues with testing, and kind of an overview of the test. So we've placed a ton of yardage. I did my quick napkin calculations here to convert it from cubic yards to cubic meters, but all in at this point, we currently have some other projects running what we consider our 7.0 modulus of elasticity and PSI, but that 48 GPA modulus of elasticity, we've done about 40,000 meters of that since 2016, and then stepping down, we've done about 20,000 meters apiece of lower rated 45 and about 40 GPA modulus of elasticity. Early on in the process, we decided that we did not want to sit by idly, even though this is an expensive test and it's a very time-consuming test. We did invest in all the required apparatus and testing systems. We now have two to actually to perform our own ASTM C469 compliant testing. So the picture you'll see on the right is actually the test being run. You generally use a traditional 4x8 inch concrete cylinder. Just to give a quick overview, you generally make a set of 3 for acceptance age on whatever given break date you use. And then one specimen is broke, or 2 specimens are broken. That test, those compressive strengths are averaged. You take and run the cylinder up to approximately 40% of the overall compressive strength, and you do it within this rig. So that extensometer you see on the right here simply measures as the cylinder is loaded how much of a movement change you have. And I'll show you later the other secondary portion, which includes the Poisson's ratio. But this is the test, and there's a lot of very exciting tests within the construction industry. Unfortunately, modulus of elasticity is not one of them. You run the cylinder up and you run the cylinder back down in a controlled load rate, so there's no explosion. There's no big fancy end of the test. It's quite boring in case you ever actually witness it. One of the first things we learned when we were going through this process, specifically for quality control, was how important cylinder casting, cylinder storage, and cylinder preparation was. So according to ASTM, if you want to process for modulus of elasticity, you should ideally be grinding, because generally your cylinders are going to be over that required strength where you can use either bonded or unbonded caps. Now, just a bit of warning on that. ASTM can be circumvented slightly if the producer were to label the mix design well under the actual design criteria. So if you were to label it, say, an 8,000 PSI mix, you technically don't need to grind it. But in order to achieve the flatness that we have found, we strongly recommend, and we grind all of our specimens here at Prairie. You can just kind of see here, it's not a great picture. This is a ground cylinder, so you can see the exposed aggregate up here, where this one slightly higher in overall length and still has a bit of that rough texture. One of the other big challenges with these cylinders that we found is we tried numerous actual consolidation methods when we were placing this. Generally, this concrete is going to be a high spread concrete. It's going to border on SCC. I would not call it a true self-consolidating concrete, but we typically ran this without any sort of slump indication, and it was measured specifically by us and by the third-party testing lab as a flow recommendation. So we would specify, depending on whether they were puddling with the mix or they were pouring major forms, a tighter flow spec, and then generally a higher flow spec. The most comfortable level and the most consistent level we found was between 24 and 27 inch spread. So that's generally where we spec the placements flow for these types of mixes. But part of the search behind that was, as you can see from these two cylinders, it gets very difficult to accurately and quickly place the rig on the cylinders if the cylinders are packed with a lot of voids or a lot of bug holes. Part of that is to make sure that you're minimizing to the utmost extent the amount of entrapped air you have in the cylinders. So the glassier kind of smooth finish you can get on the concrete, it's much easier for the technicians to actually do that. And that way, should any sort of jarring event happen during the loading process, the individual rig, which you'll be able to see in the next picture, the pins that hold it in place are not going to be jarred and completely ruin the test. So over our experiences, we have found in trialing both traditional rotting methods, using a vibrator, and simply filling the cylinder in lifts and then tapping throughout, that we find the best results with solely tapping. And I'll show you why in a bit, but it has to do with displacement of aggregate within the cylinders. So unloaded, here is what the Modulus of Elasticity rig looks like. To mention those pins that I talked about before, these are what actually bind the rig to the individual cylinder. You want those to be free floating, so these bars eventually are loosened so they are not in any way restraining movement, because you want to measure all the actual length change from the probe that would be inserted and labeled right here. But those voids that I showed you in the last section tend to get tripped up if they're on the edge or even close to, or the pins tend to get tripped up if they're close to those voids. And here's just a picture of what it looks like. This wasn't an actual Modulus cylinder. You can see there's a ton of voids in there, but that was just to fill it, to give everyone a better idea of what we're working with here. Once you actually insert the specimen to be run, we have two different machines. This is actually our slightly older machine, but if you strictly want to run the Young's modulus setup, it only requires one probe measuring overall length contraction. Again, we run that up to 40% of the overall compressive strength average from the two mate cylinders that we had already broken. Do that 3 times. The system we use now is completely automated, so we just plug that number in. It takes it up in a controlled load and it takes it down in a controlled load. It's very important because when all this testing started in 2016, very few local testing labs were actually set up to have machines that had a controlled unload feature when they were running this test. And we found that that tends to add a lot of abuse to the cylinder, which ultimately gets you very diminishing returns as you go from the first to the second to the third peak run of the ASTM spec. So should you be working with a testing lab, make sure that they actually have a true Modulus setup so they can run it completely under controlled unload and load. The picture on the right gives you a better idea of what it looks like if you are looking for the Poisson's ratio setup. This simply just has another extensometer put in there, and so this one's actually going to measure expansion of the center of the cylinder. Again, we remove any sort of, the struts stay in there, but they're completely unscrewed from the binding. So they can move, the 3 rings can move freely, and it's not a very interesting test, although a lot hinges on it. So to go back to what I was discussing about earlier, and what Lloyd talked about, a huge concern in the majority of modulus of elasticity, while some comes from overall pace strength, where you're going to derive a lot of that value is from your aggregate. Chicago is a limestone dominated market. Most of our local materials are limestone. As you start to get into other states, particularly southern Wisconsin, you will see a prevalence of gravel. We'd never opt to use gravel in modulus of elasticity due to bonding issues and overall just weaker strength. However, we're usually pretty well off with our local limestone. They have fairly high specific gravities, decent angularity, and our gradations generally are pretty consistent, but it's something that as a producer of this type of material, we need to keep on all the time. I have our technicians run, when we're producing this type of work, anywhere from 3 to 5 gradations a week to ensure that we're making any sort of adjustments to maintain those high modulus of elasticity ratings in the concrete designs. But the cylinder on top, I'm going to point out for 2 specific reasons. When we tend to see any sort of outlying modulus of elasticity results, either a kind of a funky result from a previous test or a low result from a mix we generally have had good control with, the first thing that we tend to do is to cut the cylinder. Cutting the cylinder lets us know one specific thing. If you can see in this top cylinder here, although this had a very high modulus of elasticity rating, that was generally from the use of a trap rock, which was used in this material. So early on in one of our first projects, we were unsure if we could consistently make that 48 to 52 GPa modulus of elasticity rating. So we initially started with a 50-50 blend of local limestone and trap rock from the northern peninsula of Michigan. We found eventually that the trap rock was very hard on the customer or the contractor's pump and on their pipes. So we eventually moved away from it as we moved up the building and saw that the limestone was sufficient, although the comfort level was less than what we initially would have liked. But what we found often when we had kind of squirrely results were you would find voids in the cylinders where there was not a good distribution of coarse aggregate. This trap rock in particular was very angular, much more angular than we would have liked. So we would often find aggregate bunching in certain areas where there would be distinct voids of aggregate. And over time, we determined that we thought that was primarily from the use and the practice of rotting cylinders. So we moved away from that. We initially moved to vibrating, but then found that that still would occasionally leave voids within the cylinders that could throw off our results. So we moved to simply tapping the cylinders and then finishing with the strike off on top. And we found that these cylinders tend to give us not only the best results, but the most consistent result, which allows us to better track our own aggregate sources. So in this cylinder, we see very few areas with large lack of aggregates, and we see a pretty decent blend overall. The biggest challenges in our experience in producing this type of work is the contractor and the testing lab. You have to be very careful when you cast these specimens. It's much more sensitive to movement, to initial curing, to storage and handling than a compressive strain specimen. One of the last projects I showed you, we had numerous incidents where the customer would get either a low compressive strength or a low modulus of elasticity, and we would go to the lab to review the results just to do a quick audit, and they were putting cylinders out and not storing them in any sort of controlled fashion. So they would be found out on the street. They were not water cured. They were not temperature controlled or anything like that. And the cylinders actually self-desiccated to the point where they caused fractures within the cylinder. So they were getting both low results and low modulus of elasticity. So aligning your test methodology and the lab of records test methodology is a huge benefit because you at least know you're on the same page and you're doing things the same way. So it's much easier. I strongly recommend, should you try to partake in any of this, you make sure you have proper conditioning for cylinders, proper storage, whether it's the expensive cooling boxes, whether it's just tanks of water, because these mixes, even if you are targeting massive concrete considerations as well, have a tendency to be run very hot and to break down within the cylinder on their own, self-desiccate, other sort of natural striking features that you don't see in traditional concrete. So trying to head that off in pre-pour meetings, in initial testing evaluations is a great way to save yourself headaches and a lot of time and labor spent in trying to solve the issue of concrete that's not actually defective. So in conclusion, high modulus of elasticity concrete can consistently and confidently be produced by a lot of concrete producers, but it's a team effort. You're going to need to work with your contractors, you're going to need to work with your structural engineers and your lab of records to make sure everyone's maintaining consistent, proper testing procedures to the best ability. We all know construction sites, there's never really an ideal place on a construction site for testing, for storage, for water, for any of those features that we really need, but the extra effort needs to be given to this type of concrete to make everyone's life a little bit easier. As a producer though, you have to take the deliberate steps both to protect yourselves and also to establish clear guidelines with all relevant stakeholders. There very well might be a huge cost markup for only a handful increase in, overall GPA rating. For us, going from that 45 up to 50 was really the cutting edge, And we had numerous discussions for some of these projects about them actually being in the 50 to 55 range. And once both the structural and our contractor heard the price that we would need in order to produce that concrete, they dummied that down a little bit just because it was unpalatable to them. So again, just a lot of communication up front and a lot of conversations about what can and can't be produced can make everyone really start out at a good, consolidated, and also unified relationship at the beginning. So maintain as much communication as possible. And with that, that is all I have.
Awesome. Thank you, Nick and Lloyd. We have a couple questions. I know it's 2:01, so if you have to leave, you have to leave. But just quickly, Nick, you talk about tapping the cylinders to make sure that the aggregate's well distributed. But how does this relate to the in situ MOE? Like, do you ever have to verify it in situ, like in relation to the vibrating on site? Yeah.
Fortunately for us, we have never had an in situ incident up to this point. It is a major concern for us because along with aligning the cylinders and what we could possibly do, we are not confident that if we had to take cores from an in-place form, that we would be able to accurately or satisfactorily even run a test on that. So we tend to run these mixes with a lot of either viscosity modifier or retarder just to help hold that paste very robustly to minimize any sort of aggregate segregation. It's something that we're very much aware of, and we have had instances where customers have over vibrated and or added super plasticizer on site, and they've had to essentially trim off anywhere from a few inches to up to about half a meter's worth of the top of the concrete because they overworked it and the aggregate fell out, and the structural and the engineer of record immediately knew they would not have the required rating on that portion.
Interesting. Okay. And then also typically we see a lot of variation in strength. So it might be designed for, let's say, 60 MPa, but the concrete supplier is targeting a higher strength, so let's say 70. You kind of touched on that NEMA tower and how it goes from 48.3 to 45.5 to 43.1. How important is it that it's like right on 48.3? Like, what are the repercussions if it varies?
So we actually had this conversation with a number of structural engineers because when they initially presented the specs to us, they presented it as both an average and a minimum, and they used the same value for both of those. And we told them, that the test itself is a pretty variable test per ASTM. Even within an individual test, you're allowed 300,000, I only know in PSI, 300,000 PSI difference, and it's still a valid test. So it's the amount of practical experience and application. I don't think we've reached a point where we can really have a high level of reproducibility. So they eventually did kind of give us a leeway on the bottom end that the minimum is usually about 5% lower than what they want for the average to help us achieve that. But for instance, a lot of the mixes we used almost identical mix designs, even though there was that variation in there, and we usually just adjusted the water cement ratio or adjusted some of the supplementary materials to kind of tier it down in the way we did. But we very much over designed for all of the mix designs because of our lack of experience initially with these projects.
Right. But in terms of like, if it is over designed and then you're not getting that amount of movement, is it really affecting the height of your floor, let's say, and you have to, and the contractor is going to have to adjust for that? Have you seen that?
We have not run into that where someone has been concerned about essentially it being too stiff or about the height of the floor.
Okay. Lloyd, what about you? Do you have any comments on that?
Well, when, as you well know, Stacia, we were involved in this a lot at Atrio. And again, it was to be able to compensate for the setting of the floors, so that in fact we got flat floors. It wasn't for sway. And again, the consistency that was looked for in order to predict for the presets, you have to know this in advance. So that graph, the chart that I showed on my slides of variability, we were within plus or minus 8% of the design value on a consistent basis as we measured, and that was over somewhere in the order of 1.5 years of production.
Okay.
But it did involve an awful lot of quality control measures at the start. One of the things Nick talked about was the testing. Absolutely. I had people that were using neoprene caps on the cylinders and figuring out they could measure the MOE. And of course, now we got 2 different materials that we're measuring. And the other thing that they weren't preparing them properly, as Nick was saying, so we got them to get a grinder. So in fact, the surface was plain and was consistent. The other thing that was, as far as a production basis, we had issues with the production, where one is the source of the materials varied, and so we had to ensure that we got consistent results from the source. That's of the coarse aggregate. The other thing we had is with the batching of the concrete. There were batching problems where we were getting variations in the amount of sand versus stone in our mix, and it was due to the way that they handle the materials, the way they distribute the materials up the conveyor belt, the way they put them in from the stacker into the various bins. But these are all things that if you measure it on that manner, then we spent a lot of time at the plant going through things. But if you were looking at my chart in the initial bits, we had quite a bit of variation, but then we really zeroed it, so it worked well. But they were concerned if it got too much, we'd be having really problems with our presets, because you have to think in advance, like 150 days in advance. Where's it going to be later? And so it's important to get that consistency, and that was one of the things that was hammered out. That's very important. So you have to be able to demonstrate that. So you have to have a system where you are measuring on a regular basis the effect of your modulus elasticity.
Right. Okay, I think that's it. Thanks both of you. Tomorrow we have 2 presentations that you can still register for if you'd like. And again, ACI-Ontario thanks everyone for their support during these challenging times. We're going to continue to look for ways to bring you concrete-related technical information sessions, which on that note, if anyone has any ideas for future presentations or would like to present on something themselves, you can email us at ACI-Ontario at gmail.com. And then we also hope to hold our AGM virtually or in person, depending on how things are going, sometime in January 2021. So thank you all for attending.